Okay. Yeah, welcome everyone to the 61st meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Giovanni Cerulli Irelli from Rome, and he'll be speaking to us about Motzkin combinatorics in linear degenerations of the flag variety.
Thank you, Rudradip, for inviting me to speak in this seminar, and thanks to everyone who is attending it for coming. I want to present work with Francesco and Esposito and Mario Marietti. You find the preprint version of this on the arXiv. It is number, let's see, 2112 02539. And it will appear soon on IMRN. So let me start with an outline of what I want to talk about and what this project concerns. So there is, for every n, we are interested in a special family. So this family is a subfamily of so there is here some representation variety of a quiver, RDQ, and above there is the universal quiver Grassmannian. So pi inverse of M is the variety of subrepresentation of a fixed dimension vector of M, but this doesn't matter. I will explain all of this. And inside here, and Q is a quiver of type A equioriented. And inside here, there is an open subset that let's call it UN. And this open subset corresponds to what is called the flat irreducible locus of the linear degeneration of the flag variety, but this doesn't really matter. So there is, by restriction, there is here a map, and this family is, so pi is, and pi n is flat. So every fiber has the same dimension and proper. So fiber are projective varieties. And the total space, this Xn, is smooth and irreducible. Smooth and irreducible. Okay. And moreover, there is the action of the structure group that we call GD, and the map is equivariant. And there are finitely many orbits. And this map here is called linear degeneration of the flag variety, of the complete flag variety. So let's call it just FLN. So this one here. Okay, and now we apply the BBDG decomposition theorem. So we take the push forward of the constant sheaf on Xn, and then we shift it by the dimension of Xn, and then this sheaf decomposes into direct sum of IC intersection cohomology sheaves on the orbit closure with coefficients in Q, and O is orbit. So this direct sum is over the GD orbits in this UN tensor with some graded vector space. And of course, O bar means the Zariski closure. Okay. Yes. Right. Now look, let's take a point N, in here in UN, and let's look at the stock here and also here, and let's look at the cohomology of the stock. So let's consider H dot of so the stock here at n is just the fiber over n, so it's just by n inverse of n. So this is just the cohomology of the Grassmannian of n, and this decomposes as the cohomology of these IC sheaves on O bar coefficients in Q over n tensor VO. And now the direct sum is only over the orbits containing n in the closure. Okay. So here I just applied, you know, wait, can you see? Yes. Okay. I'm just considering the stock of this sheaf at n and then taking the cohomology. And now, look, there is, suppose that, that's not going up. Oh, yeah, it's going up. Okay. And now there is, suppose that n belongs to the orbit closure of some m. Then there is a specialization map that, let's call it CMN, between the cohomology of the Grassmannian of the most degenerate point into the cohomology of the Grassmannian over the more generic point M. And there is this result of myself together with Fang, Fourier, and Esposito from last year, saying that CMN is surjective. Yes. So I'm going a bit fast. I'm sorry, but well, okay. Anyway, I cannot really see you, so please, if you have any questions, so just interrupt me, okay? So there is this map. This is just an outline. I will try to. This is motivation. So this map is surjective. So it has a kernel which is graded vector space. And now consider the only minimal degenerations. So suppose that n is in the closures of, say, T representations. So n, so this symbol here means that n belongs to the orbit closure of Mi. So this is GDMI closure, and this is minimal. So in the covering, in the relations that is the orbit closures, this is just a covering. Okay, so minimal. Okay, now then what happens is that we have specialization map CMIN from cohomology of the Grassmannian of n into cohomology of the Grassmannian of Mi, and this map is surjective by this theorem. And then we can consider, and this map is a homomorphism of graded rings. Okay, so So the kernel, so then we can consider the kernel of this map, MIN, and then take the intersection from I from 1 to T. Okay, so this is on the left side of the story. So it's just here on this part. But now let's see what happens here on the right part. So on the right part, so so let's see. So here we have to take direct sum of IC of of cohomology of IC of bar yes bar say Q then N and tensor VO, and then direct sum of H dot IC of bar MI Q tensor VO. Okay. Okay. And now let's look at O equals ON here in this sum. And for every I, there is a kind of CMIN restricted to O from IC O bar QN into IC O bar MI, well, sorry, O bar Q. Sorry. MI, yes, so QMI. So for every O, there is such a map, okay? For every O, there is such a map here. Let's look at O equals ON. Then, of course, this is just Q. So what is CMIN ON? So the orbit of N. Well, this goes from Q, because then if we plug in here, we just get Q tensor VON into zero, because there are no orbits between the orbit of N and the orbit closures of N. So, okay, so ON is not contained there, right? Okay, this is just to motivate the following fact, that if VON is non-zero, then the intersection of the kernel of the map CMIN is non-zero. Okay. And of course, knowing the intersection of the kernel is very important, because suppose that inductively you know the cohomology of this more generic point of the this Grassmannian here. You want to know the ring, the cohomology ring of the Grassmannian of N. Then it's important to know what is the kernel, the description of the kernel. Okay, and so definition, we say that O is a support if VO is non-zero. So having a support has something to do with knowing the cohomology ring of the fibers. Somehow it has to do with this. And then beautiful theorem of Fang and Reineke. Um, 21, that appears in Documenta Mathematica. Says that there is a function that in our paper we defined FR for Fang-Reineke from the set of Motzkin path of length n to un up to ISO. So to the orbits, the GD orbits in UN, which restricts to bijection between mod n and the support of pi n. Okay, so let's see, let's go back for a moment. So we have this map. Pi n that I didn't define. I will tell you more, of course, about this. So, and here in the base there are finitely many orbits, and then we apply the Bernstein, Bellinson, Deligne, Gabber decomposition theorem, and then we ask what are the orbits in UN such that VO is non-zero. Okay, and then the beautiful theorem of Marcus and Kin says that, well, these orbits are parametrized by Motzkin path. I will give you the precise definition, but by now, in this just in this introduction, mod n, so is a Motzkin path from 0, 0 to 0 n. So it's something like this. It starts from 0, it can go northeast, it can go east, it can go southeast, but it cannot go below the x-axis. So something like this. So this is 0, 1, 2, 3, 4, 5, 6, which is our n. So this belongs to mod 6. Okay, and then this project with Francesco and Mario started from the, well, we were very ambitious. Okay, so we wanted to not only say what is the support, but we needed to know, we wanted to know what are the coefficients. So what are the VO? So the aim is to understand coefficients VO. So not only the orbits such that VO is non-zero, but also for those orbits describe this graded vector space VO. So this graded vector space, we expected something like the cohomology ring of some variety. This is what we expect. To understand coefficients VO. So what are these graded vector spaces appearing in the decomposition theorem? And then this is very ambitious, and so our first aim was to understand better the map of Fang-Reineke, because this Fang-Reineke map is a kind of min-max function. So it's not trivial, it's actually difficult to understand, given a representation, if this belongs to the support or not. And also given a Motzkin path to describe what is the representation, it involves some computation. I mean, this map is very clear, I think, to my co-authors. To me, they are it's a bit less clear. The proof of Fang-Reineke's theorem passes through the Knight-Zelevinsky duality, and also kind of heavy computation in canonical basis. It's a beautiful result. So the first aim, sorry, it doesn't go. So what we needed is a better description of the orbits in the support. And then what we prove, so theorem So myself with Esposito, Marietti. So OM, say this is the orbit of a point. M is in the support, so is a support. If and only if M is an excessive multisegment. So we give this purely combinatorial definition of what is an excessive multisegment. Of course, this is the heart of the talk. So that's the main definition of the talk. So this is a combinatorial object. It's very easy kind of verify if a multisegment is excessive, and this is our characterization of the Fang-Reineke map. Okay. So to do so, we have to kind of algebraize the whole picture, this geometric picture that we have, and put it into combinatorial terms. So now, if you don't have any questions, I would go into the actual paper and to the actual talk and start with some combinatorial model. Okay. So you understand there is this map, we want to understand the support, and then we describe the support by combinatorial data that we call excessive multisegment. Okay, very good. So, 1, the Motzkin monoid. So definition, let me call the definition of a Motzkin path. Motzkin path. Gamma of length n is a function gamma from 0 n, which always means 0, 1, n, to integer, such that 1 gamma I is always non-negative. Two, gamma 0 and gamma n are 0. And 3, the difference between gamma I plus 1 and gamma I cannot exceed 1. So example, for example, we go up, then down, then up, 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 down, down, then we stay, we go down, then up again, and so on. Okay, so here is the axis. Is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is n. And we denote by mot n the set of Motzkin path of length n. By mod 0 is just 0. Mod 1 is just the flat one. Okay, so this is 0, 1. So it's in particular mod 0 and mod 1 are singleton. And then we consider the disjoint union of all of that. And we call it mot. And then it turns out that this set, this graded set, has a binary operation. say from mod P, mod Q into mod P plus Q for all P and Q less or greater or equal than 0. And this operation is called concatenation. We call it concatenation, and this just take Motzkin path, take another Motzkin path, and put them together, all after the other. Okay, so it's called concatenation. Okay, since half an hour is already gone, and I'm still in section 1. Maybe I don't give you the example. If you don't understand concatenation, then you just ask me, okay? So the only the only thing I want to say is that, so remark, observation, concatenation is associative, and mod 0 is the identity. So then this means that mod with this operation is a monoid. Okay. And also graded monoid. So this is a graded monoid. So the operation is a graded operation. Okay, so this set of Motzkin path as operation. So just you take two Motzkin paths and put them together. And then there is a suspension. So there is also a unary operation. There is also, we define a unary operation S from mod to mod that we call suspension. So why did we call suspension? Well, from the name, maybe you can guess. How did we define it? You take some Motzkin path. For example, let's say this. So this is gamma. Then what is as gamma? Let me draw the axis. Then I use all the power of this machine to copy the path and then paste it here, but not in 0, but you see a bit above 0. And then in order to make it a Motzkin path, we have to add these things here. So this gamma, this belongs to 0, 1, 2, 3, 4, 5, 6, 7, 8, mod 8. And this one now belongs to mod 10. You see, we had to add two extremes. So S is degree 2 map. Okay. Very well. Yes. So now easy an observation remark. So gamma in mod. Well, okay, first of all, is called primitive if there are no non-trivial Motzkin path, delta and epsilon, such that gamma is the concatenation of delta and epsilon. But then you see, by concatenation, we said we just put all them together. So it means that if something is a concatenation, it must touch the x-axis in the middle. So in particular, the suspension of Motzkin path cannot be concatenation. So suspension of a Motzkin path is primitive. So then we notice that as gamma is primitive for all gamma. Okay. And then we have the following proposition. Mod with this operation is a free graded monoid generated by S mod. And then of course we have to add mod 1, because since this is since S is a degree 2 map, of course mod 1 cannot be in S, and of course it is primitive. Okay, very well. So that's the first, this is the Motzkin monoid. Do you have any questions so far with the...
Can I ask a quick question?
Yes, Lucas,
so isn't
please.
the converse also true? So a Motzkin path is primitive if and only if it's a suspension?
This is true. Exactly.
Yeah, okay.
Exactly. This is precisely what this proposition is saying. Exactly. Thank you. Yes.
Ah, okay. Thanks.
Yeah, absolutely. So generated by means that, yeah, these are precisely the primitive elements. Perfect. Thank you. All right. So what is the universal property of mod? There is the following universal property. So suppose, so this is the second part of the talk, very important. Suppose that you give me a monoid, which is graded. So suppose that let M be a graded set, graded by the positive non-negative integers, endowed with a binary operation, with binary operation, let's say dot from M times M into M, which respect the grading. So it restricts to a map from MP, MQ to MP plus Q. And suppose that this map and it is associative. So suppose that we have a graded monoid. And suppose that this graded monoid is such that M1 is cardinality 1. This is very important. And also that is endowed with unary operation from M, and there exists S from M to M of degree 2. Let's call it not S, but curly S, okay? Then first thing, there exists a unique homomorphism of monoid let's call it phi from mod to M, commuting with suspension. So such that if we take phi of S of gamma, this is the same as curly S of phi of gamma for every gamma in mod. Okay, so this is the first thing. So there exists this map, and this map is unique. And unicity basically comes from this fact that M1 is just composed by one element. Second fact is that if the suspension, this curly S is injective, and the image of S is contained in the primitive elements of M, then phi is also injective. Okay, so if one knows that the image of curly S is composed by primitive elements, then and S is injective, then one has for free the fact that this map, which is unique, is also injective. The third map is that the third condition, the third thesis is that phi is bijective if and only if S is injective, and the primitive elements of M with respect to this operation are precisely the suspension union M1. All right. So that's the universal property of this Motzkin monoid that we found. And why do we want to use it? Well, remember what was our motivation? We have this map of Fang-Reineke, this one, going from mod n, look, from mod n to isoclasses of quiver representation. And then what we want to show is that this map is actually preserving suspension. And then we want to give to this set, so this is a finite set because there are only finitely many isoclasses for each n. So we want to give to this set the structure of a monoid. Okay, so that's now our logic. So we want to give to this set the structure of a monoid. So 3. So multi-segments. So we fix n like this, and Q is the equirented quiver of type AN, which for many of you probably seems very trivial, but it's actually a very interesting object. Yeah. So quiver of type A equirented is still interesting, even if we know everything about the representation theory, but it's still it has questions that are not answered about it. Okay. Okay. So the indecomposable representations of Q modulo isomorphism are in bijection with segments in 1n. So for example, take the representation which is 0 everywhere, and then C, and then 0, blah, blah, blah. This is, say, vertex A, vertex B, and identity everywhere. This corresponds, of course, to the segment. And by corresponding, you just take the support of the representation, okay? So there is a bijection between these two. And so there is a bijection from the representation of Q modulo isomorphism to multi-segments. Just union of segments, okay? So for example, let's take this representation, take dimension 4 everywhere. And then let's fix a basis. So these are basis elements. And let's take, for example, this representation. I hope you understand the thing. Then, of course, the multi-segment is 1, 2, 2, 3, and then there is one simple here, and then one simple here, and then two copies of the projective injective. Okay, so I hope this is all fine. And now for us, so by dimension of M, this corresponds to what we call weight of the multisegment, just to give a different name, but it's just the dimension vector. So for me, this is a multisegment, okay, but this is okay. So this is okay. So for now on, by the n, it will be just dimension vector n plus 1, n plus 1, n plus 1. Okay. And RDQ is just direct sum of n plus 1 matrices. So it's just Cn plus 1, Cn plus 1. So from say over n minus 1 arrows. Okay, so this is the representation variety of dimension vector n plus 1, n plus 1, n plus 1. So for example, for n equals 3, then we need 4 dots in each vertex, and then we just have to choose some segments random. So this is a point in RT, or another point is, for example, this, which is just 4 copies of the projective injective, and so on. So this is the variety appearing as the base variety of the universal of the linear degeneration of the flag variety. Okay, and now I define the family that I'm interested in. I take E. So remember, D always denote this dimension vector, and E will always denote this dimension vector. Okay, and then we consider the following variety, X, A, D, to be pairs U1, UN, and then Fi from Cn plus 1, Cn plus 1. So here I goes from 1 to n minus 1, and Ui is a vector subspace of Cn plus 1 of dimension I, which is Ei. And the incidence condition is that Fi of Ui is contained in Ui plus 1. And then there is a projection map into RD. We just take, say, U, F, send it to F. So that's the map that I defined in the first section. Okay. And then what is the fiber over a point? So pi inverse of M is what is called the Quiver-Grassmannian. It's just collection of vector subspaces, one for each vector space, one for each vertex, and which are compatible with the linear maps. So for example, if M is, so example, and this was an observation of myself with Fang and Reineke from 2011. If one takes the Grassmannian of just this representation here, where the identity everywhere, this is just the flag variety, the complete flag variety, because you see, there is line in the first space, plane in the second, tree space in the third, and so on. And all of this must be compatible with the identity. But this means that the line must be contained in the plane, that must be contained in the tree space, and so on. So this is precisely the flag variety. And then all the other fibers of this map are then called linear degeneration of the flag variety. And then there is the following theorem. by myself, and then Fagin, Fourier, and Fang and Reineke. When was it? 14. That says that so the locus where the map pi is flat. So this is all the M in RD such that the dimension of the fiber over M is equal to the dimension of XAD minus the dimension of RD, which equals to the dimension of the flag variety. So this is the locus where the map is flat, is always open. And well, this locus actually is equal to UN, which is by definition is the set. So this is all the M in RD such that the multisegment associated to M has at most one cut per column. But there is this beautiful combinatorial description of the locus where the map is flat. You take the multisegment of weight n+1, n+1, and so on, and then look up the cuts. So so cuts means that the rank grows by 1. Okay. So for example, for 3, so this has one cut. So this is no cut. One cut, 2 cuts, 3 cuts. Okay. So in this case, UN consists of these 2 orbits. Very well, very well. Now time is almost up. Okay. Okay, and now, yes. So as I said, what we want to do is to give to the set of multisegment of weight D the structure of a monoid, and this we do. So let me just okay. So we take so monoid of multisegments. So we take R to be the set of multisegments Rn, multisegments of weight D. Okay. And then in this set, this is a finite set, we give the structure of we define a binary operation on these sets and a suspension, which I don't have time now to define, but I hope to give you. Okay. And this Rn is not free. It's a graded so, and then we take so Rp, Rq, Rp plus Q, and this goes to Rn plus Q. Then we take the union of all this Rn. So then this is a graded monoid. It's not free. Okay. Then inside so inside R, we consider M multisegments having at most one cut per columns. And here by universal property of the Motzkin monoid, what we prove is that there exists a unique injective homomorphism of monoids from, let's call it phi, from mot to M. So this locus, this flat irreducible locus, is very, very special also from the combinatorial point of view, because it's a free graded monoid where the suspension is injective and such that the suspension of elements is contained in the primitive elements. And now, what is the image? Of this map, of this injective map? And well, this is precisely what we call excessive multisegments. We don't have time now to define excessive multisegments, but let me just say that we define inside E some what we call excessive multisegment, excessive multisegments of in M. So this is a submonoid of M. This submonoid is now free, and the map phi restricts to a bijection between mot and E, so that the image of phi is equals to E. And now the theorem is proved once we prove that Fr from mot to M is a graded homomorphism, is a homomorphism of graded monoid commuting with suspension. Well, but then by unicity of that map that we define, by the universal property of mot, this map must be factored through E. And then we get our theorem. We get our theorem, and this explicit description of the image gives us a way to also to have a kind of more concrete description of these supports. And then the next step is to understand coefficients. And I stop here. Thank you very much for the attention and for being still here. So
Thank you. Thank you, Giovanni. Can we all please unmute ourselves and give the speaker a round of applause?
Yeah. Okay, thank you. Yes.
Okay. Do you have any questions? If you have any questions, you can either unmute yourself and ask, or you can put them in the chat.
So I'm a bit confused about one thing. Could you go back? I think it's on a previous slide.
Yes.
We defined RD.
RD. Oh, yeah.
The variety RD.
Yes.
Maybe I'm just confused, but shouldn't you mod out the action of the general linear group, this product of general linear groups acting on all these CNs?
Well, RD is just the affine space on which this group acts.
Yes.
And then when we factor out the action, then we get just the isoglasses. So
yes.
we get the set of multisegments.
Okay.
So you're right.
Okay.
This does not belong to RD.
Okay. Okay. So that's intentional.
It's an isoclass. So I should say it corresponds to an isoclass contained here.
Okay.
But yes. So
Thanks.
this RD is just an affine space. It actually is the easiest representation variety of a quiver that everybody knows, but still there is this interesting family on it, and then this interesting parametrization of the points. So yeah, thanks for the questions. Yes. So that's...
Thank you. Any other questions? Well, I had a comment / question myself. So you ended with this theorem where you showed that the map FR is this unique graded monoid homomorphism permitting suspensions. Exactly. So in your paper, I saw that there was what you called a final application where you looked at FR inverse and you gave a way of computing it recursively. Yes. So is there any hope of proving a theorem exactly like this for FR inverse where you describe it formally?
Yes, this is excellent question. We were trying to reprove Fang-Reineke theorem by using our description of this map. So because you see, we have this map phi. Now we have this map, but we don't know that the image is in the support. So that the image corresponds to the support. So that's what is missing. And we have some kind of ideas on how to prove it, but it's very, very hard. And Fang and Reineke had to work a lot to get that. They had to pass through computation with canonical basis and Knight-Zelevinsky duality. So, but we are working on it, and so yes. Thank you.
So just to be clear, you do have the fact that the supports correspond to these excessive multisegments, but exactly. You want something stronger.
Exactly. Excessive multisegments are something that you draw the multisegment and then you see this is excessive. But instead, if you take a multisegment, checking that this is in the image of the Fang-Reineke map is not easy at all, because it's a min-max function. So that's somehow the idea. Exactly. Yes.
Okay. There is a question from Kyla Wright in the chat. Can you see it, Giovanni?
Yes, thank you for the question. So what other things are counted by Motzkin paths? It's plenty of things counted by Motzkin paths. And now we realize that the reason for this is that there exists a Motzkin monoid with that universal property. Somehow this could be an explanation why Motzkin numbers are so sparse in mathematics, because of this universal property of the Motzkin monoid. Whenever you have a monoid which is graded and having a suspension of degree 2 and so on, and then there is a unique map from the Motzkin monoid to that monoid. And so many things are counted by Motzkin monoid. One can construct a Catalan monoid, for example. This could be in the same spirit that we did, and we also have a universal property for that. And but about Dick monoids, I think we didn't. I don't know if my co-authors are still here. If they are, do we know about something about Dick monoids? I don't know.
I think Francesco is here.
Yeah, so I think there. So Catalan numbers count Dick paths, and there's a monoid. I mean, which is responsible for the combinatorics
of course
Dick paths.
Yeah, of course, Catalan numbers count Dick paths. Oh, sorry, yeah, of course, yeah. So one can construct the monoid corresponding to Catalan numbers. So meaning that the n graded part, the n homogeneous part has cardinality the nth Catalan number. Yes, thank you for the questions.
Yeah, thank you, Kara. Any other questions for the speaker?
Sorry, I might have missed that, but what again was an excessive multisegment?
Yeah, I didn't define it.
Ah, okay.
So it's a multisegment that does not contain triples like this. So let me give you an idea. Does not contain triples of segments like, for example, something like this. Or something like this also. So whenever you have to look at the multi-segments, and then you don't want configurations like this. And the way why my creative and genius co-authors ended up with this definition of excessive is because they knew what should be in the kernel of the specialization maps. And if something contains these triples, it cannot be, I mean, the specialization map is injective, so it cannot be a support. So this is how we end up with this very strange definition of excessive multisegment. Excessive is called excessive because it adds something on the cohomology of the previous one, on the more generic one. So if something is excessive, it means that there is it's adding its cohomology ring of Grassmannian, of the corresponding Grassmannian, as something more than the cohomology ring of the Grassmannian attached to more generic point. So this is why we call it excessive. So
okay,
so this strange definition comes from this naive, naive story that I told you at the beginning, that the supports are contained in the kernel of the specialization map, and we have an idea what should be the kernel.
Great, thanks.
Yeah.
Okay. Any other questions? Don't see. Yeah, I don't see any other. I'm not seeing any other questions in the chat or. Yeah, I'm not seeing any other questions. Well, in that case, let's thank the speaker once again for this very wonderful talk.
Thank you. Thanks everyone for coming. It was really a great pleasure for me. Yeah, I hope to meet you in person at some point.
Yeah, just a minute. Let me stop recording. Just.